Hello everyone, so today we're going to be discussing logarithmic functions and some of their properties, and then getting into how to evaluate different logarithmic functions, and then applying concepts such as limits and integrals to them to evaluate also. So first we're going to start with a few different properties, and this might be a review for some, but the first one is going to be if b is greater than 0 and b does not equal 1, we can write f of x equals b to the x, which is either increasing or decreasing function, and therefore is 1 to 1, as we discussed in the section previous to this. Now what we can also say is that given these conditions, right, log base b of x equals y, and that's going to mean the same thing as b to the y equals x. They imply each other. So here we have log base b, so that's the base of this function. And then the way I like to think about it is base answer exponent. So if you want to convert it into this form we see here on the right, if you think about b, a, e, then it's a little bit easier to do that. So we see here we have the base b, so that's going to be the base right there. The answer is x, so that's going right there. Then e means the exponent, that's y, and that's going in the exponent spot right there. So that's a good way to memorize that. So a few other properties to note are these here. So we have log base b of b to the x, and that's just going to equal x. So those b's kind of cancel each other out there. And then likewise we have b to the log base b of x equals x also. So these are the cancellation equations, and those you'll need to know also for different methods of evaluation. Next we're going to look at a few other properties, which again might be reviewed for you, which is that log base b of xy equals log base b of x plus log base b of y. And here, in this one, we see that the multiplication can just be split up over addition there on the right. And then something similar for when we have an example of division. So we have log base b of x over y, and we'll split this up over subtraction. So log base b of x minus log base b of y. And then finally we have this one right here, which is log base b of x to the power r, some real number r. And then now we can rewrite that as r log base b of x. So we see we're just bringing that r right down over here to the side. That's what the properties of logarithm allows us to do. So those will also be some that you'll need to know for a few of the examples we're going to practice. Next, we're going to look at a few of the limit properties involving logarithms. So just label this section, so limit properties. And if we have, so let's just say if b is greater than 1, which we discussed earlier, then we have two different conditions. We have limit as x goes to infinity, log base b of x equals positive infinity. And then we also have limit as x goes to 0 from the positive direction, log base b of x equals negative infinity. And then the last part we're going to look at before we start getting into examples is the natural log. So we have natural log functions, and then here's some of the properties of these. So we know that log base e of x equals ln of x, so that's denoted natural logarithm, denoted ln of x. And then we can write ln of x equals y, these are just some random variables. And we can rewrite that as e to the y equals x. So what ln does is it allows us to kind of get rid of that e. Alright, so for the first example, we're going to look at the directions are pretty simple, and it's just going to be solve for x. So solve for x. And the first question we have here is ln of x squared plus 1 equals 3, and we want to solve that for x. Well, remember how I discussed in the last property we went over about the relationship between natural log and then base e. So if we have natural log here on the left, we can add in the base e to this and exponentiate ln of x squared plus 1. So first step is we're going to add base e and then raise ln of x squared plus 1. We're going to put that all in the exponent power, so then we just have e to the 3. So all we did here is just added this e value and that e value there and raised everything into the exponent. So that's what e allows us to do, is exponentiate the function. So at this point, we know that e and natural log cancel one another, so we're just going to cross those right out. And now we have x squared plus 1 equals e to the 3. So now it's just a simple algebra problem. We'll subtract 1, those cancel. So then we have x squared equals e cubed minus 1. And now we just got to take the square root of both sides. So taking the square root, we have x equals, remember square root is plus minus, square root of e cubed minus 1, and that's as simple as we're going to go. We don't need to use a decimal. And that's the answer to this first one. For the next example, the same thing. We're just solving for x. So this time we have 1 plus e to the 4x plus 1 equals 20, and we're just solving for x. So first thing is we see that 1 sitting out there on the side by itself, so we can just take that, go ahead and subtract that from both sides, and that's going to give us e to the 4x plus 1 equals 19. Now we have something familiar, very similar to what we worked with last time, except we're going the different direction now. We're not going to exponentiate, we have to get the 4x plus 1 out of the exponent. So for that, we're going to take ln of both sides, so natural log of e to the 4x plus 1 equals ln of 19, and we know ln and e are going to cancel each other out, so we cross those right off, and then we have 4x plus 1 equals ln of 19. Now, simple algebra problem, just like last time, subtract the 1 from both sides, they cancel right there, we get 4x equals ln of 19 minus 1. And then we just divide both sides here by 4, and that gives us x equals ln of 19 minus 1 divided by 4. And that's our final answer for this one. So the last example for these types of problems is going to be a little bit trickier. Same instructions though, solve for x. This time we have ln of 2x plus 1 equals 2 minus ln of x. And we just want to solve for x. So first we're going to get all the ln terms on one side, such that ln of 2x plus 1 plus ln of x equals 2. So now we just have that 2 hanging out there by itself. And we can rewrite this, remember, based on the properties we discussed before. We can get rid of this addition sign here, and we can combine those over multiplication. So we'll rewrite this whole thing as ln of 2x plus 1 times x equals 2. Again, that's just using the property we went over at the beginning. And we can combine these further such that ln, we're just distributing the x inside the parentheses there. So ln of 2x squared plus x equals 2. Now we have something that's a little bit more familiar. and we can write this using e, because we got to cancel these things out. So we'll exponentiate the ln of 2x squared plus x. So we have e to the power ln of 2x squared plus x equals e squared. Now we know ln and e are just canceling each other out, so cross those off, and we're left with 2x squared plus x equals e squared. So at this point it's a little bit trickier than before. It's not just dividing by something and solving for x. So now we're just going to subtract e squared from both sides, such that we have the whole equation equal to 0. So we have 2x squared plus x minus e squared equals 0. At this point, this is not an easily factorable quadratic, so we're going to use the quadratic formula for this. And remember, from algebra, that's x equals negative b plus minus square root of b squared minus 4ac divided by 2a. So we have, this is a, that's b, that's c. So at this point, we're going to plug right into that formula, and we have x equals negative 1, because we're just taking, again, the coefficient, so we have the 1 is the coefficient there. So we're just taking negative 1 plus minus square root of 1 squared minus 4 times a, what's a? That's 2, times c, which is negative e squared. So we're taking that whole negative e squared term and putting it in the parentheses there. And divide by 2 times 2, because a is 2. And then we don't need to simplify this down a whole lot. We'll just rewrite this so we have the bottom half multiplied out. So we have x equals negative 1 plus minus root 1 squared root, no, that's just 1, minus 4 times 2 is 8, so we'll just write minus 8 times negative e squared. And actually, we're just going to write that as plus 8, because negative times a negative is positive, so plus 8e squared, divide by 4. And that'll be our final answer. Next, we're going to look at questions involving limits. So these are a little bit trickier than what we're just doing. The instructions still pretty simple. It's just going to be evaluate for these next few problems. But the problems themselves are a little bit more complicated. So the first one in this type is going to be the limit as x goes to infinity of e to the negative x squared. We just want to evaluate that. First, what we're going to do is we're going to let t equal negative x squared. Now we know we can rewrite this whole thing as limit as x goes to infinity of e to the negative x squared can be rewritten as limit as t goes to negative infinity of e to the t. And this is coming from those properties that we discussed at the beginning, those few limit properties we talked about. And we know so let t equal negative x squared, so as x goes to infinity, t goes to negative infinity. Again, this is coming right from the properties we discussed earlier. So now we're just evaluating limit as t goes to negative infinity of e to the t, exactly what we see right here. So it just simplifies everything. So we think about that, the exponent blows up and goes to 0. So the limit of this whole thing is 0. And again, that's given by the property we discussed earlier. So this is a more general example of a limit property. Next, we're going to evaluate this one here, which is limit as x goes to 2 from the negative direction of e to the 3 over 2 minus x. And we want to evaluate this. So again, we're going to let t equal what's in that exponent, so the 3 over 2 minus x, so let t equal 3 over 2 minus x. So as x goes to 2 from the left, we know t goes to positive infinity, and then that's going to be by the properties that I already was mentioning. So again, we're going to do the substitution. So limit as x approaches 2 from the left, e to the 3 over 2 minus x is going to equal limit, and again we're switching this here at the bottom by the substitution we discussed right here. So that's going to now become limit as t goes to infinity of e to the t, and we know that goes to infinity. And that's our final answer. Alright, for the third limit example, we have limit as x goes to infinity of e to the 2x divided by 1 plus e to the 2x. So here we need to try and simplify this down some. And the way we can do that is multiplying the top and the bottom by 1 over e to the 2x. And that's going to cancel it out at the top. So let's write down here. So we'll multiply by 1 over e to the 2x. And that's going to give us limit as x goes to infinity of e to the 2x over 1 plus e to the 2x times 1 over e to the 2x divided by 1 over e to the 2x. So you notice when we multiply this term here by that, they cancel out and we get 1. And then this by this, we have 1 plus e to the 2x over e to the 2x. So that's going to help us simplify this down a little bit. So after that, we get limit as x goes to infinity of 1 over 1 plus e to the 2x over e to the 2x. And we'll rewrite this as limit as x goes to infinity of 1 over e to the 2x plus 1, because we see we can split the numerator there over the addition. So specifically we're looking right here, we can split that up over addition. So really all we want to focus on is this term right here. We know all those other ones are just 1, just a regular 1. So the only place we're checking the limit is really just right there. So we know that e to the 2x as x goes to infinity, that goes to 0. So that blows up and goes to 0. And as such, limit x goes to infinity of 1 over e to the 2x plus 1 equals 1 over 0 plus 1, and that's just 1. So 1 divided by 1 is 1. And that's the final answer for this. So next we're going to look at some integrals involving these types of problems. So the first one we have here, and that's just going to be evaluate. And the first one we're looking at is the integral of t cubed e to the negative t to the 4th. So that's a little bit of like a nested exponent up there, and then dt is our constant of integration. So remembering from Calc 1, the best way to do this is going to be a u substitution, where we let u equal this value right up there, and if you notice, once we differentiate that, it becomes a little bit easier. So let's u equal negative t to the 4th. Now du equals negative 4t cubed dt. At this point, we see we have the t cubed term right there. We have a t cubed term there. So what we're going to do is we're just going to divide both sides by a negative 4. and that will leave us t cubed dt on that one side. So if we can rewrite that as negative 1/4 du equals t cubed dt. And that's the form right here that we really want to focus on. So we can rewrite that whole integral as negative 1/4. We're just going to keep that outside because we're really doing nothing to that part. It's easier just to keep it factored out. And then all we have left is e to the u du. Because we know negative 1/4 du equals t cubed dt. So that goes away, all we're left with is e, and we know this term equals u. So all we're left with is e to the u du, and this is a very straightforward integration problem from here. So that's just going to be 1/4 times e to the u plus c, and then we'll just plug in our u value here. 1/4 e to the negative t to the 4th plus c. And that's our final answer for this one. So there's a u substitution. A lot of these with the exponents like that, when you see a base e, that's a good indication that you might need to use u sub. So the next one we'll look at here, problem 2, and that's going to be evaluate, and we have e to the x times 4 plus e to the x to the power 5 dx. Now, for this one, we're going to let u equal 4 plus e to the x, so everything on that inner term right there, so this inner term right there, we're going to let equal u. And then we know du, that 4 is just going to go away. And we know derivative of e to the x is just e to the x, so e to the x dx. All right, and this is matching up pretty nicely because we have e to the x dx right there, and we have those terms over there too. So now we're good to proceed. At this point, we have integral u to the 5th du, and this is a very straightforward integration problem again, so that's just going to be 1/6 u to the 6th. Plus c, because we don't have any bounds that we're evaluating at. And now we just plug in our u value back into this. So we have 1/6 times 4 plus e to the x, all of the power 6 plus c, and that's our final answer. So again, just do u substitution. And our last problem we're going to look at for integration and for this whole section is going to be integral of 1 plus e to the x squared divided by e to the x dx. And this is going to equal, we're going to expand out this term on top, and I know the first instinct is probably to do a u substitution here. But not yet. We need to wait on that because I know the instinct is probably going to be to do a u sub of this, but that is not going to work out. So we need to expand this term right there. So we know that 1 plus e to the x times 1 plus e to the x equals 1 plus e to the x plus e to the x plus e to the 2x. So that's just going to equal 1 plus 2e to the x plus e to the 2x. And that's what we're going to move and put down here. So we have 1 plus 2e to the x plus e to the 2x divided by e to the x, and then we have our integral there, and then constant of integration dx. Alright, at this point we can split this up into 3 separate integrals over the addition. So we see we have an addition sign right there and another one right there, and we have 3 terms on top. Well, we can split that up into 3 integrals, 1 over e to the x, 2e to the x over e to the x, and e to the 2x over e to the x. So 3 different integrals, and then it becomes a very easy problem to solve. So we'll go ahead and do that right here. We have first integral of 1 over e to the x dx, and then we just keep the addition signs, so plus, and then we'll go ahead and factor out that 2 of the 2e to the x term just to simplify things. So 2 times e to the x over e to the x dx plus integral of e to the 2x over e to the x dx. And from here, we're just going to simplify this even further such that we can rewrite 1 over e to the x as just e to the negative x. So e to the negative x dx plus 2, we know this whole thing here just divides out equals 1, 2 integral 1 dx plus dividing these 2 is just going to leave us with e to the x dx. Now we're going to let u equal, for the first one, we're going to let u equal, so I'll just break this up into 3 different ones. So first, we'll let u equal negative x, du equals negative dx, negative du equals dx. And now we're evaluating negative integral e to the u du. And that's our first integral. And we know that just evaluates to negative e to the u, which we know u is negative, or we know u is negative x. So this is just negative e to the negative x. So that's for the first integral. Second, we don't need to use substitution. This whole thing is just going to equal 2x. And then third, we just have e to the x, because we know this here just evaluates to x, this evaluates to e to the x. And then we just need to add our constant of integration when we combine all these. So we're going to combine all of these cases right over here, such that negative e to the negative x plus 2x plus e to the x plus c, and that will be our final answer for this problem and conclude our topic for today.